Welcome, this is SS Tripathi from the channel SST Chemistry, welcoming you once again for the second video on organic spectroscopy problem series for PG students and NET GATE aspirants. In the first video published in the last Wednesday, we had discussed 5 problems within 41 minutes, but this time I will be discussing 7 problems of the past NET GATE problems, NET GATE questions. But I will try to restrict the time to max 30 minutes. I can't promise because it will no longer remain under my control, however pace I may make. Now the first question is like this: the number of signals that appear in the broadband decoupled C13 NMR spectrum of phenanthrene and anthracene respectively are. Just you pause the video and you try to find out how many carbon peaks will be found in phenanthrene and anthracene. Then match with my answer. If you put only one mirror plane at the middle here, only one middle plane symmetrically at the middle of this middle benzene ring, you will find these two are interchangeable, these two are equivalent carbons, 1 1. These two are equivalent, so 2 2. And so also these two are equivalent under symmetry operation, plane of symmetry, they are interchangeable, so they are equivalent carbons. Because this is carbon resonances, we have to also consider the quaternary carbons. So this is 4 4, they are equivalent. 5 5, and this is 6 6, this is 7 7. So you will get 7 carbon peaks, singlets, because it is decoupled, no coupling with protons. But in case of anthracene, you have 2 mirror planes. One is vertical, please don't mind, it is I'm not able to draw perfect lines, so please bear with me. And there is a horizontal mirror plane, so with respect to this vertical one, so these two are equivalent, and with respect to the horizontal one, these two are also equivalent, so also these two. So all these 4 carbons are equivalent, right? Similarly, these two are equivalent carbons, so also these two under this horizontal. So these 4 carbons are equivalent, so also protons. But here in carbon we will be including the quaternary carbon as well. Now these two are equivalent under horizontal plane and these two are equivalent under vertical plane. So this, they are equivalent. Under 2 planes you can explain. And finally this one, the 9 and 10, these 2 carbon atoms lying on the vertical plane, they also on the horizontal plane, they're interchangeable, and they're also sitting on the vertical plane, so they will give you another set of carbons. So in anthracene you will get 4 carbon resonances, 4 peaks, but in case of phenanthrene you will get you will get more than that, 7. So the correct answer is 7 4. Let us go to the second one. I have drawn it here in a better way so that you can get the file. I will be putting the link to get this file downloaded, so you can do that. So my construction of this diagram will be very, very weird, so therefore this ones will help you more. Now the second one, in a 400 megahertz proton NMR spectrum of an organic compound gave a doublet signal. In a 400 megahertz proton NMR, from carbon we have moved back to proton. An organic compound gave a doublet signal. Two lines, that means two components of the doublet, are at delta 2.35 and 2.38 ppm. Then what is the coupling constant? You know from your undergraduate level, if you are an undergraduate student, you also know that supposing this one is the TMS position and we are having a 100 megahertz field strength, that is 1.4 Tesla, and you are getting a certain doublet here at say 2 and another doublet at 3. And with respect to the TMS position, how do you know the delta nu in hertz? This is the ppm small delta that you know, and therefore this will be under 100 megahertz field. This one is 100, so the delta 2 ppm will be at delta nu, and this mega and 10 to the 6 will cancel out, and this 100 will go here to 2, so it will be 200 hertz. This one will be 200 hertz, and the 3 will be undoubtedly, this one, this is supposing nu 1, this is nu 2, this is nu 1, and this is supposing nu 2, that will be nu 2, that will be 300 hertz. But if you increase the field to 400, these will be spread out. These will be spread out, but the ppm will remain the same. With respect to TMS, this doublet and this doublet, they will be spread out, and this time 400 will be there. So 400 into 2, the difference will be 800 hertz, and this difference will be 3 into 400, 1200 hertz. So this will be the chemical shift in hertz, not in ppm. ppm is 2 and 3 once again, and you know that the coupling constant is the small little gap between the component, the two adjacent components of a multiplate. So that never changes. Whether you increase or decrease the resonance field conditions, so J value is independent. It is a scalar through bond coupling. It's nothing to do with the external magnetic field. So that difference, is given this one is given 2.35, and this is 2, supposing one is at 2.35, and the other one is, the other component of the doublet is 2.38. And what is the, difference in terms of ppm? So it is only 0.03. That is the difference in the two components of this doublet. This is in the ppm, so that into 400, that is 12 hertz, will be the J value is not expressed in ppm, it is expressed always in hertz. It is, since independent of external field, it is always expressed in hertz, but the chemical shift positions with respect to TMS is always expressed in ppm, right? So the answer is 12. Now coming to the third one, which is again very interesting one, where only the proton NMR data is given. An organic compound, a proton NMR data, 7.8, 2 proton doublet, J 8 hertz, 6.8, again 2 protons doublet, 8 hertz, 4.1, 2 proton quartet, J 7.2. So, and 2.4, 3 proton singlet, and again 1.25, 3 proton triplet. That means the compound has 2 methyl groups and 1 methylene groups, and these 2 PICs stand for the aromatic protons. So since there are 4 aromatic protons, it is to be bound to be para-disubstituted. So as we already have discussed, so this is this A dash and this will be say X dash, right? A dash, sorry, so this will be A dash X dash. Why I am saying X dash? Because this is electron withdrawing group and this is electron donating group. And more importantly, this, supposing our compound has ethoxy, it is much more electron donating by R effect, resonance effect. So it has to be para. Para will give you 2 proton double doublet and 2 proton double doublet. Here the J4 coupling with this 1, 2, 3, 4, 5, J5 coupling is not observed. 1, because these two are chemically equivalent, so they do not couple. 1, 2, 3. So this will be only doublet for this, but I am talking of the J5. 1, 2, 3, 4, 5. So there is J5 is almost 0, so it will be giving a doublet, and this will be also giving a doublet at the upfield position. This will give you a doublet at the downfield position in the aromatic region. But first thing, the starting point is 4.1 peak, methylene peak, which is so high. 4.1 can never ever be a methylene bonded to carbon. It has to be a methylene bonded to oxygen. That also we discussed in our last video. So out of the 4, you have only these 2 which has got O bonded to, supposing I will split out CS2, CS3. So a methylene is bonded to O only in these 2, ethoxy, para-ethoxy acetophenone. But here it is not acetophenone, it is 1 para-ethoxy propan 1-one. So our we have and we have only 2 methyl proton peaks. So here there are 2 methyl proton peaks, and here also there are 2, but there is an additional methylene peak, this methylene and this methylene, and there will be another quartet. There is only 1 quartet and there is a 1 triplet, so there must be another triplet, another quartet. This methyl and this methyl, they are not equivalent. They are supposed to give different peaks. They may be very close and they can coalesce, they can overlap, but there is no such indication, clear-cut indication is not there. It is definitely not this one. So without any doubt, our correct answer is this, not this, not this. This we have already cancelled out because there is a phenolic OH group. There is no mention of 1 proton peak is not there here. The question doesn't arise. And since 4.1 is our starting point, we need a CH2 bonded to O. And we can assign this 2.4 peak is the methyl protons which is directly bonded to carbonyl group, right? This aromatic ketone should be a 2.4, and this one, if we split this into ethoxy, this is the 4.1, our starting point, and this one is a quartet at is a triplet at 1.25. So this triplet, this quartet at 4.1, and the other one is a singlet because there is no neighboring proton at 2.4. That's it. And the question of this doesn't arise because there will be an additional quartet and triplet and quartet. There is no such thing. And the 2.4 peak is a 3 proton singlet. Here it is 2 proton. So in all consideration, the correct answer is this. A is the correct answer. Now coming to the next one, this is very one. I have just introduced the first time the problem on IR spectroscopy. Now there will be a little variation because when you eat some food, you have so many other ingredients, accessories, spices. So to make our conversation, our discussions spicy, of course spice level should be not close to 10. It should be less spicy so that it will be good for our stomachs, tummies. Now look to this one. Correctly match the structures with IR carbonyl stretching frequency in the following table. Now this one is a ester. Cyclic esters, as you know, are called lactones. And the only difference is that there is a pi bond here, and here there is a pi bond here. Since it is a 5-membered ring, a normal lactone is supposed to be little more than aliphatic or acyclic esters, like 1750 60 is the range of an aliphatic ester without any conjugation. Now if there is a 5-membered, it will be little more, maybe 1770, 80, like that. And here there is a double bond which is in cross conjugation with the lone pair. This lone pair, one of the lone pairs, will be conjugating here and also conjugating here. This is the allylic position, so that there are 2 cross conjugations. As a result, what will happen? The conjugation to the carbonyl group will be lowered. In other words, whatever conjugation was there in the neat compound without any additional double bond, that will be decreased because of its association, conjugation with this pi bond. As a result, the double bond character will be more than this. So, and this one is very interesting. Here is also there is cross conjugation. Here there is one conjugation, and the lone pair is other conjugation. So both the conjugations will make more single bond character, and the spring constant of this oscillator will be the minimum, and R will have the minimum one. Where is the minimum? Minimum, this one. This X, R should be connected to X minimum. And the maximum here, because of the opposite side resonance, the carbonyl resonance is a little less possible, so that there is a more double bond character here. So this should be the maximum. So R should be connected to Z. Now obviously the neat one, the without any double bond, the neat butyrolactone will be definitely in between. So undoubtedly the P is connected to Y. So out of all these, you find P is connected to Y, Q is connected to Z, and R is connected to S. So this is the correct answer. So there is a less resonance here because of the added resonance on the opposite side. There is a double resonance here to the same side to make it more single bond character, and this will be less single bond character, more double bond character. This will be the control where there is normal conjugation is there. And most importantly, conjugation is not the hallmark of esters. It is the minus I effect which is more dominant here to make it 1700, 60, 50, 80, like that. But for a comparison purpose, we have to take the resonance into account and finalize that the maximum one is this one and the minimum one is this one and intermediate. Now coming to the next one, this is very interesting. C13 NMR spectrum of acetone D6, which is used as a solvent. Now we are taking it as a compound to have a spectrum, or else in any other compound, the acetone D6 gives a signal, the solvent signal, at 30 ppm as a septet in the intensity ratio. Once we say septet, we think of the Pascal's triangle, that is the coupling with 6 neighboring protons. Might be CH2 on one side, no, CH3 on both the sides. So 3 plus 3, 6 plus 1 septet. We are reminded of an isopropyl group. Now it's a carbon resonance. Remember, carbon is spin half, but deuterium with which it will couple, this is the deuterated acetone, that is acetone D6, and carbon will couple with deuterium having I is equal to 1. I is equal to 1, and since I is equal to 1, the magnetic quantum numbers are -1, 0 and +1. There are 3 equally populated states. I is equal to 1 for deuterium. Since it has a small little quadrupole moment, that is electric quadrupole moment is small, so the coupling is there. And this is unlike protons spin half, where there are literally 2 protons, means you can have in the middle energy consideration, you have 1 up, 1 down, like this. The other probability is 1 down, 1 up. Such a thing will not arise inside the nucleus. The 3 possible spin states, -1, 0, +1, or whatever, maybe 3/2 nucleus, whatever the magnetic quantum numbers are there, they are equally populated. So always 1:1:1. Supposing there are 5 states or 4 states, 1:1:1:1. That is inside the nucleus. Unlike different nucleus, then it will be, probability factor will come. Here there will be no probability factor. So Pascal's triangle is not used. Here a different table is used, that is called trinomial triangle. This is Pascal's triangle for spin half, but since deuterium has equally probable nuclear states, -1, 0, +1, then we have to use another triangle. Now just to make a deduction how we go from 1 to 2 to 3, supposing there is only one coupling deuterium to carbon. So it will be 1:1:1 triplet that you find if you take deuterochloroform CdCl3 at 77, you get a triplet, not 1:2:1, 1:1:1. So we just ignore, we know 77 is to be ignored. And in many data they never give, they remove from the spectrum. But while we study the spectrum literally, then we ignore that solvent peak. And if there are 2, like dichloromethane, deuterated dichloromethane, CD2Cl2, then further each component will be further split into 1:1:1 component. So by merging here 1, and from here 1 and here 1, this becomes 3, this 2, this is 2, this is 1, 1:2:3:1. And if there is another third deuterium, so this, each of the components will be further split into 1:1:1, so that when it merges from all the directions with the same coupling constant, then you will find 1:3:6:7:6:3:1. But how to remember this? So the Pascal's triangle is now replaced by trinomial triangle. Here what you do, you write 1, you put 2 zeros on both the sides, left and right, then add from left 3 digits, add 3 digits from left, and write the result on the second position. Leave 1 0 and write in the second position. So 0 0 1, the sum is 1, so write in the second position of this first, not here, the second position you start writing 1. These 2 zeros have been given later, so first you write 1 here, then leave this, Then next 3 digits 0 1 0 is 1, right? 1 here below 1. Then leave these 2 zeros 1 0 0 1, and then nothing to be written, that is all. Then add again 2 zeros in the left and 2 zeros in the right. Then do the same thing 0 0 1, the sum is 1, right from the second 0 below it 1. Then 0 1 1, that becomes 2. Then 1 1 1 3, 1 1 0 2, then 1 0 0 1, that is the quintet that we find in this one. CD2Cl2, we get a quintet at the corresponding carbon. I have not given the carbon resonance pick, it's not a common solvent, so I didn't find. Doesn't matter, you get a quintet, not in the ratio 1:4:6:4:1, 1:2:3:2:1. So, and there are 3, then again add 2 zeros here. Then 0 0 1 becomes 1, you start from the second 0. Then 0 1 2 3, 1 2 3 6, 2 3 2 7, then 3 2 1 6, 2 1 0 3, 1 0 0 1, and they go on adding 2 zeros on both the sides. Do the same business, you'll find the nonnet on decade. You can do that theoretically, but we never come across with such solvents which can give you deuterated solvents which can give you a nonnet or on decade. This is theoretical progression of the trinomial triangle. So so that is the thing, DMSO-D6. And for your information, that DMSO-D6, acetone D6 solvents, when used in proton NMR, sometimes we get a quintet peak, proton peak at 2, same intensity ratio 1:2:3:2:1. Why? Because in the deuterated solvent, there is an impurity, small quantity of impurity containing a single proton in each spin system. So this single proton gives a proton peak and coupled with 2 deuterium to give you quintet. So the 2 ppm proton peak appears as a quintet in this ratio. That is due to the impurity present in the DMSO-D6 or deuterated acetone, right? So in this kind of discussion, I will be sharing with you my experiences so that it will enrich your confidence, I'm sure. Going to the next question. The Larmor frequency of proton at 1 Tesla is 42.57 megahertz at 1 Tesla. If it is 1.4 Tesla, it is 1.4 Tesla, it is 60 megahertz. And if it is 2.3 Tesla, it is 100 megahertz. So 1 Tesla proton resonance takes place at 42.57 megahertz. The magnetozyric ratio of proton and carbon-13 are this and this. And it is almost 4 times less. Carbon-13, by mass, it is bigger, 13 times bigger. But by magnetic property, gyromagnetic ratio, the G factor, it is nearly 4 times less. Radians per Tesla per second. So the Larmor frequency for carbon-13 in the same 1 Tesla field will be how much? Obviously, if it will be 4 times, the gamma is 4 times less, then the resonance frequency will be nearly 4 times less divided by 4. But to do exactly, the Larmor frequency of hydrogen, the basic NMR equation is gamma. This is new. This is gamma. Don't confuse. This is magnetozyric ratio into B0. B0, it is magnetic field by 2 pi. And so also this is carbon, Larmor frequency. Gamma carbon, B0 by 2 pi, B0s are same, they're cancelled out. So ultimately, we have the ratio of the Larmor frequencies is equal to the ratio of their magnetozyric ratios. So these values are exactly given. So the ratio is 3.98, not 4. 4 was just an approximate one. So that carbon resonance will be 3.98 times less. So it is coming 10.695 approximated to the first place of decimal 10.7. So this is the correct answer. So you can get it. These are very simple problems. This is the correct answer. I hope you understand. Now, this one is the last one before we close today's session. I think it will be 30 minutes one. I have not seen my watch while I started. The fluorine NMR spectrum of chlorine trifluoride when measured at minus 60 degrees Celsius will consist of the following NMR signals. This is not proton NMR, not carbon NMR, but fluorine NMR. It has got its own resonance frequency. You know, it is little less than proton frequency because its gyromagnetic ratio is little less than that of proton. If proton is 100, then it is sometimes 90 something, 92 or something for the fluorine nucleus, fluorine NMR. So, when you are looking at fluorine, and you know chlorine will be useless for splitting, although it is a spin, nuclear spin is non-zero, quite high, but it has so high electric quadrupole moment. The quadrupolar interaction is so high, chlorine, bromine, these things. You know, they make rapid relaxation so that most of the nuclei remain in their ground state. They are not distributed in all different states so that it sees only one state, because the rapid relaxation occurs due to a villain that is called electric quadrupole moment. And also there is electric field gradient vector. So we'll not discuss about that. That makes the relaxation very efficient, for which we do not get any coupling with chlorine. So chlorine means you forget. So only fluorine, we have to look to the actual shape of chlorine. If you go back to your +2 stage, you remember that chlorine trifluoride is a T-shaped molecule and the chlorine atom is sp3 dehybridized, where one fluorine atom is sitting at the trigonal base, the other two corners are occupied by lone pairs, and the other two fluorine atoms are axial. One fluorine is horizontal, that is equatorial, and the other two positions are lone pairs, and the other two fluorine atoms are equatorial. But at room temperature, there is a rapid intercombustion between the one equatorial proton and two axial protons, so that you get a sharp singlet. But at such a low temperature, when the flipping or the interchange becomes less, totally restricted, prohibited, at that time it shows two types of fluorine atoms. So these two axial ones, which are longer, they are equivalent under a symmetry operation. And this one is another one which is non-equivalent. The distance is less, 160. So you get two fluorine peaks side by side, two fluorine resonances. For this it will be a triplet, because there are two equivalent neighboring fluorine. So this fluorine will give you a triplet, and these two equivalent fluorine will be giving you a doublet. So a doublet and a triplet. This will give you a triplet. Oh, sorry. This will give you a triplet, and these two, which are equivalent, will give you a doublet. So a lot of side information is required. Not that only one subject, like say you are going to answer a problem on group theory or whatever. So you have to have other knowledge where group theory is applied in different fields, right? So the correct answer is doublet and a triplet. Now usually if you don't think of the non-equivalence of the three fluorines at such a low temperature, you will find it will be a singlet. But actually it will be giving two fluorine peaks. One is a doublet and the other one is a triplet. Maybe very close to each other. Maybe they will not give you a proper fast order spectrum. It may be a pseudo fast order. All these things we will discuss, no doubt. This is simply a problem solving sessions, but my theory sessions and other sessions will come. So in every week I will be meeting you. So how did you like this one? And please, you're not giving comments. I know, so definitely you might be liking. Might be, I said might be liking. So if you're liking, why not you push the like button, so that I'll be encouraged to do more videos for you. And if you do not subscribe, then you can't get notification. Every time I can't send to individual persons. Even if some of you are known to me, I can't, it's not possible to send every time. So it is better that you subscribe. Bye. See you next week with more problems. Bye-bye.